Uh, Good afternoon and welcome to our SIG HPC Education Chapter webinar. I'm Steve Gordon. I'm currently the second Secretary Treasurer. And I just wanted to remind you about a couple of things before I introduce today's speaker. The first is please renew and pay your annual dues. It's only $10 for professionals and $5 for students. And you can do that at our website. But there's a caveat, and that is a couple people have informed me that at least over the weekend, their website was having problems and they wouldn't accept their money. So I've reported this to ACM and hope it'll be resolved soon. And I will send a note out to the membership as soon as I hear back from them that it's resolved. Secondly, I wanted to remind you that there's another webinar next week, October 19th at noon, code.org and bringing computer science to all. From one of the staff at code.org, and I hope you'll join us for that. I will be sending out a reminder with a link to that site and also place that link on the chapter web pages as well. And finally, we because of changes in how Google is doing this kind of broadcast, we've had to introduce another place for you to chat with us, to answer questions. I'll bring this back up at the end as well. But if you have questions, you can post them to the chat, and you just log in with your name in parentheses, no passwords needed. I'll hold those questions till the end of the broadcast. So this will give us a way to answer any questions you have. So with that, I'm going to, whoops. I'm going to turn it over to Bob Panoff from the Schroeder Education Foundation, who will be talking, giving our webinar today. So Bob, I'll turn it over to you.
Great, thank you. So a lot of what we're talking about in computational science, in computational thinking, is something that for many of us we are trying to do. Steve, can you confirm the slide is actually showing there? If anything comes up and it doesn't look quite right, just let me know.
So unless I interrupt to say otherwise, it's okay, okay?
Great, that'll work. So if you can see on the screen here, the topic of this is computational thinking for all. Next week's topic is computer science for all, but the idea of the computational thinking encompasses using the computing, but it also requires a lot more of the cerebral gray matter, what we often call grayware, so to make sure that we have this sense. And we'll talk a little bit about what I call the power and the peril. What are the strengths and what are some of the weaknesses that come in? There is a link to this talk that will have at least the HTML version of the slides available, and we can send that out again at the end if people are interested. So when we usually talk about computational science and computational science education, I often am moved to introduce two breathing modes. One is computational science education, which is using computers and modeling to teach the content of chemistry, physics, biology, mathematics, geology, psychology. It's usually running code that already exists. It's not so much building and writing code or writing models, but it's using computational tools to explore and teach the content of science. There's also computational science education, which is actually doing exactly what we had said, which is teaching people how to build the model, how to run the code, how to test the model, talking about errors and error propagation, looking about parallelism, looking at different types of things. And that's a very important part of what we do as well. I don't think we need to talk too much to this group about why we use computation at all. This idea that with experiment and theory, any model that we have today, even if all you're doing is adding up the numbers and dividing by the number of numbers, that's a computation. And failure to do that correctly, especially when there are large numbers of numbers, when you get into big data, that suddenly big data brings up questions about round off and truncation that we didn't realize were there, because so many things have been added together that the next individual contribution may not even matter. It may not even show up in the data. So we're going to talk a little bit about, the computational parts of this and how we can sort of move forward in what we're doing and how we're doing it. So I want to start off talking a little bit about what the computational thinking is as opposed to the programming. And that is that the thinking individual, when given a tool that allows for dynamic manipulation of a computational model, that you also have sufficient power to recompute and revisualize the model, not necessarily in real time with the largest problems, but at some point the dynamic and interactive nature is part of the thinking that needs to go on. And at the same time, either through expert systems or through actually humans who are expert, having the ability to interpret and understand the model as well. What I like to say is this word in the English language of representations and representation is really something to emphasize the computational aspects. By changing the model and representing it, then multiple representations help really form the understanding of the multiple representations. And so whether the model is presented in a visual format, as a graph, as a series of graphs, as a dynamic graph, as a table, as a visualization which uses color and spectral density and variation, all of those things are interesting from a particular standpoint. So what I'd like to do is to show an example of something that is developed at Shodor, sort of runs anywhere, goes anywhere, and says, what if you had some data? So here is some data, and that data could be taken into a tool that is dynamically exploring that data. And if I change the window to emphasize more of the size of the data, then I'm going to put some light grid lines on here. The question is, what does this function look like? How would I determine the actual model that this empirical data is giving to me? How could I do it in a dynamic way? Obviously, this is nonlinear data. For a lot of our students, and again, I'm sure everyone in this audience recognizes at least the general form of this, but for those that don't, we can actually bring up the shapes of nature. When is nature linear or quadratic? When is it Gaussian? Or when is it something that has some particular set variable that you can find a shape if you don't know it, and then we can use that to sort of accelerate the process of understanding data. Now, this is something that Excel would not allow you to add a trend line, but since what we're actually doing is individually, numerically, evaluating for every data point the distance between that data point and the fit, then we can go through here and just look at the data and look at the curve, and then dynamically ask the question, what is a better representation? Do the bumps need to be bigger? Do I need to have more bumps? How many bumps do I need to have? Do the bumps need to move left or right? Here it appears to be the bumps are much too granular, so I could make a more sensitive fit to the data. And then even there, you can see in this particular data that it appears that one set of values appears to be better if I'm modeling the endpoints, and a different set of values appears to be better if I'm modeling the points that are in between. Now, to make that even more dynamic and visual, what I'm going to do is physically build a square in which the side of the square is the deviation between the data point and the point that I have in mind. And so by creating a square whose area is the square of the deviation, then I can come back here and say, if I'm looking at the middle data points, I get better fits in the middle than I do at the ends. On the other hand, if I'm fitting at the ends, then I need to be thinking of moving what I have in the middle part so that I get the middle part. So I can either fit the ends or I can fit the middle. And you can see that this is not actually a pure cosine, but it's a sine that's been modulated. But the ability of doing that dynamically and interactive, obviously for small data sets, is something that can be done on a laptop, on a server. When you're starting to talk about massive data, then this type of interactivity also is less likely to happen, but the computing load could be taken over by some kind of high performance computing. So this is just a little bit of the sense of the thinking that goes on, is to say, I can look at this and tell what's a better fit or not, and I don't necessarily have to completely automate the entire system. So the computing that we have is what we sometimes refer to as a thought amplifier. Now, how do you get this into the classroom? Well, if you want to go from qualitative modeling to quantitative modeling, the steepness of this ramp of how soon you can get students to go from running models to modifying models to writing models of their own, where you might start with a hand-waving model that talks about what's going on, or formulating the model mathematically, perhaps starting to use things like spreadsheets or agent or modeling systems, or something more advanced with a computer-assisted algebra system, or actually writing code, and asking all along the way, what does the answer look like? Or in some cases, even what does the problem look like? Your ability to do that depends upon whether or not there's curriculum that either you've developed or others have developed, whether you have interdisciplinary team skills, or whether you think every physicist, every geologist has to also be a numerical analyst and a programmer. It seems to be much better to me that if you could simply collaborate with those people, you could get much more work done sooner. Understanding the technology is an important part of what's going on here. And if you don't understand how things really work, things could be quite difficult. Your ability to think in different terms of various mathematical modeling, in which, depending on how you model something, you can interpret it in a particular way. There are curriculum barriers where, how do you get this into the classes that are already being taught, or how do we get this into new classes and possibly even new degree programs? So all of this is based on this idea of, what are your goals? How do you bring it into the classroom? And we'll talk at the end of this talk about some sources, some resources, and some people who could perhaps help you on your own campus or in your own organization. So we want to talk a little bit about where the computational thinking needs to be there. If you're really doing science, it's hard for me to imagine a case, mainly because I've been doing computation the whole time I've been from high school onward, that authentic science has to be done from a computational standpoint. And at the same time, what needs to be done is that the computational part has to be done scientifically, right? And so what I mean by authentic science is this idea of, what do you expect? What do you observe? And if you think about it, how do you know if it's right? And that's a big part of things that are going on. What I'm going to attempt to do here is go back to sharing and see if it will allow me to pick a different screen. Are you now seeing an Excel spreadsheet? I think so. So the rule is, if it's not right, you will tell me. So if I came up here and I just talked about 3/6, and I talked about the number 1/6, oops, that thinks it's a date. So we'll make it a number. One of the things that you can see fairly quickly is that the number 1/6 at some point appears to be truncated and then rounded to be represented as a decimal. In English, this could be described as more than a sixth. So the computer representing 1/6, it really represents it as something it says is more than a sixth. On the other hand, a half, 3/6, is exactly 1/2, and in a binary computer, that's exact. So I might ask you, what would you expect if I took 3/6 and subtracted more than a sixth, subtracted more than a sixth, and subtracted more than a sixth? And the computer tells you to sort of infinite numbers of decimal places. Well, actually, we're not making it infinite, we're only making it 20. That number really is 0. So when I calculate it, you might say, at one level, should I have expected to get 0? And clearly from my years of arithmetic, I would. But from this simple recognition that the computer is not able to represent 1/6, you might not expect to get that. Now, one way to show that to you is if I take this entire calculation and put the whole thing in parentheses, not changing the order of operations, not changing any associativity, but just take that calculation and put it in parentheses, you get two things that are perhaps now surprising. One is it's not 0, and the other is it's not negative. Because if I took 3/6 and subtract more than 1/6 3 times, you don't expect to get 0, and I don't, but I also don't expect to get a positive number. And that's because if you don't understand how the computer's actually doing the computing, you could be confused and have trouble interpreting numerical values in the context of a scientific model. Now, if I was to take this number, right, and combine 2 of the 6 together, I'm still taking 3/6 in total and subtracting it from 3/6, but now you get a completely different number that's not 0, and it's still not negative. Now that's evidence that when you type in a number like this, it's not actually truncating it. I'm sorry, it's not actually rounding it, but the number that's stored in memory is probably truncated, and only when the formatter represents that number as a decimal number does it round the number up, because in some ways that's what Microsoft thinks you're expecting. So your expectation of what you get in a particular calculation can be affected by your number. I'll give you another quick example of that. If I took the number 10 and 9.8, it certainly looks like 10 and 9.8 are represented as what I said they were. If I show you the next number in the sequence, it should look to you that Excel is simply taking 0.2 and subtracting it from the previous number. Okay? But what you may not realize is that as it's doing that, it's not really subtracting 0.2 because it can't represent 0.2 exactly as a decimal, as a binary number. So it approximates it. And after 7 subtractions, by the time I get down to 8.4, even Microsoft can't lie to you. And it actually tells you that, well, let me show you the number that's there, because the accumulated round off error is now so big, it just has to display it. So
but there was one comment that a person couldn't see the formulas you were typing in to get those numbers.
Yeah. So the first formula, I just wrote in 3/6. Then I typed in 3/6 minus 1/6 minus 1/6 minus 1/6. Can they see that? And again, unexpectedly, because 1/6 appears not to be exact, nevertheless, Excel lies to you or makes you feel better about yourself by telling you that it's exact. However, you can get Excel to be honest with you by putting the whole calculation in parentheses, and in that case, you see it's not 0. Now, for this example, I myself didn't do a calculation. I basically showed Excel that the first two numbers that I'm going to deal with in a sequence are 10 and 9.8, right? So I'm going to clear these out. If I take 10 and 9.8, and then in the lower right corner, grab that and drag it down, Excel says, oh, I see what you want me to do. You want me to continue that pattern. And when you can continue that pattern down, what you start to see is that at some point, you could be fooled into thinking that 0.2, the difference between these two numbers, was exact. But eventually, because of the way that Excel writes its rules for the formatter, when the error gets to be big enough, it has to print it out. Is that clearer? I hope so. If not, ask another question and Steve will stop me there. So I'm going to go back to the talk part of screen share, if it'll let me. And talk a little bit about authentic inquiry. Now, the authentic inquiry is this stage where you really, really ought to say to yourself, how do you know if it's right? And one of the things that we're finding is that students rarely take a look at a number that either comes from the web or comes from a model and spends appropriate time asking the question, how do you know if it's right? So I'll give you my classic example from the web. If I searched for the boiling point of radium, the boiling point of radium would be reported to me, according to Google, as 1,737 degrees Celsius. If I go down to the very first link, the Royal Society of Chemistry says the boiling point of radium is 1,500 degrees Celsius. If I go down to the JLab, right, the Thomas Jefferson National Acceleration Facility, it says that the boiling point of radium is 1,413 degrees Kelvin, which is 1,100. So in Celsius, is it 1,100 degrees? I don't know, if maybe make it bigger. So here's the first three links: 1,140 degrees Celsius, 1,500 degrees Celsius, or 1,737 Celsius. Now, each of those is based on some kind of measurement that somebody did at some point, and the question is, what reason do you have to believe it? And the same thing could be true of mathematical models, that depending upon what you're doing and how you're doing it, the mathematical model has to be tested against some kind of quality factor that says, how do you know if it's right? And so some of that comes from numerical analysis. That's maybe theoretical. Some of it comes from practical numerical analysis, where you change a parameter and see what effect it has on the model. And you ask, is that what you expected? Is that reasonable? And then you can also sort of build up a sense of what are the limitations of the computers themselves. You know, the details of how a chip computes becomes important. The details of whether or not in a particular system numbers are assumed to be initialized with a zero value or not. The determination of how big are the numbers. Are they single, double, or quadruple precision? Which registers are used for the mantissa, which are used for the exponent? All of those are things which are part of the thinking of computational thinking, and it's not just, you know, running the code and taking whatever comes out. Now, I want to spend a little bit of time talking about what we do and to teach computational thinking. And a lot of what we do is what I might call either pre-programming or it's programming thinking, but it's not necessarily writing syntactical procedural code. So it's not necessarily coding, but it's absolutely numerical modeling. And the two ways that we typically communicate science to others is through drawing pictures and telling stories. And I want to give you examples of both of those in the form of a computational environment in which, if you can draw a concept map, for instance, you have built the model. Or if you can tell a good story with nouns, verbs, and adjectives, you would basically have built the model. So the first example I want to give comes from an approach which is called system dynamics, in which you have 4 shapes for the concept map. You have a box, which is always the amount that you have. You have a pipe with a valve, which is what's changing. You have things that you know to be true. And then you have these blue dependency arrows, which are always the 8 English words. I need to know the start time. So the I need to know in order to compute. I need to know the amount ingested in order to compute the absorption. I need to know the absorption rate constant in order to calculate the absorption. I need to know the half-life in order to calculate the excretion rate constant. I need to know the rate constant to calculate the excretion. So that's basically what's known as a system model. There are many pieces of software that let you do that, from Stella to Vensim to Insight Maker to all kinds of things that people have written. We happen to use Vensim in a lot of our workshops because it's free for education. Now, when you do that and run it dynamically, what you've really done is written an iterative loop that solves the equation, what you have is equal to what you had plus what changed, over and over and over. The amount of plasma level that you have is the old plasma level plus what was absorbed minus what was excreted. The amount that is ingested that you have is the amount that you had plus what you intake minus what is absorbed and is now part of the plasma. And that iterative process, you can actually go directly from this picture to writing to the code, and software developers have done that. So for instance, I could come down here and increase the time of the simulation. So you now see there are 4 24-hour cycles. I could increase the number of times that I'm exposed to the toxic material in some particular number of time units. I could change the total exposure, and over time, the more exposed I am, the greater probability that I'm going to reach a toxic level in my body. If I'm a smaller person with a smaller blood volume, the concentration is going to be higher for me than someone else. But much like I showed you with the wave function and our tool called the multifunction data flyer, this particular way of modeling allows you to take every constant in the model and turn it into a dynamic parameter, so that you can actually see what's happening in the model as the result of adjusting different type. If I have a higher absorption constant, I get bigger bumps. If I have a smaller absorption constant, I get smaller bumps. If I have a longer half-life, the stuff stays in my system longer. If I have a shorter half-life, the toxic material leaves my system faster. And that ability to think in terms of the parameterization in the model that is changing over time is one of the best demonstrations of what I would call computational thinking. It allows you to do that type of thinking in a real sense. Right? So there are many, many examples of this. At the end, I'll give you a link that will have you links to links of many examples that we have for different types of system modeling and other types of modeling that are going on here. Another kind of approach, besides just the drawing of the picture, is the telling of a story, right? And so one type of way of doing this is actually using a tool that takes things that you have, and here's our story. If a healthy person is next to a sick person, there is a chance the healthy person changes into a sick person. Healthy persons not next to sick persons move randomly part of the time. Healthy persons not moving randomly actually try to get away from contaminated areas. After a sufficient amount of time, or even faster with rest, sick persons can change back into healthy persons. And this is sort of redundant. Sick persons who do not move get better faster than if they move around. That's what it means up here of faster with rest. Right? Now, if I come down here and look at this, in this model, the blue squares represent healthy persons. There are 4 red squares that represent sick persons, and all of them can move randomly, although the red ones are going to move slower than the blue ones. And then I'm also going to show you by using color that I can show you the degree of contamination in an area because of the healthy people that are there. So what you should notice is that the sick people are near other sick people. The sick people are red. You see this area of contamination. And because the health, oh, there it is. Did you see the epidemic? Did you see the burst? That because the healthy people were trying to stay away from the sick people, they bunched up. But that meant if even one sick person got in there, the whole lot. Let's randomize and run it again. You can see that people could get better faster. Boom, the epidemic happened faster. If I reset it, run it again. Now, this is only using hundreds of agents, but with real science, you're typically using thousands or millions of agents, and as a result of that, the computing requirement gets even bigger. Now, in this case, the people that are staying away have formed a little bit of a buffer of distance, and now you'll see some of the sick, oh, there it is. Somebody got in, and now everybody's sick again. But I think what you can recognize are 3 things that we've noticed with students. One is, this is a pretty cool way to model, and you can have fun. Oh, there we go. Did you see this time? All the sick people got better before any of the other people got better here. So depending upon what you have, let's see, are you seeing? No, I guess you're not. I can't tell which screen you're seeing. Hopefully it's the model screen for things that are going on there.
Yes, it's a model screen.
Okay, so if I hit the reset on the model screen and run it again, you'll see that every time you could get something different. I could use different numbers of initial conditions. I could change the rate of infection. I could change the rate of mobility. You'll notice that every time you do this, it's really a matter of studying this more carefully. I could collect numbers, do averages and graphs. And again, that's part of the quantitative part of computational thinking, is that ability of actually using numbers. There, everyone's been cured. And now all I have are the sick people, the healthy people that are there. So this is a whole piece of what's going on with both this, and what we have a finding is that even at the larger simulation scales, these approaches are used to think out the model. There's a huge project called the Massive Infectious Disease Agent Simulation, also called MIDAS, in which they're not just using a few agents, they're using hundreds of thousands, close to 1 million agents in their simulation, looking at how different diseases might spread in a population the size of the United States. There are system models that are being used to actually formulate problems of every kind. And the problem formulation of systems thinking and telling stories for the agent behavioral modeling is something that we are very much helping faculty incorporate into their classes. We have a number of examples. We have a number of units. There are textbooks that have been written that support this approach to modeling. And it really is where things are going. Again, if I go back to my friend Google and type in system dynamics diabetes, one of the things that you can see very quickly is that many people studying diabetes are using these kinds of system models to think out the progress of the disease, either in an individual or in a population, right? If I came up and said system dynamics terrorism, except I can't spell terrorism, what you're going to see is that many people are using system dynamics to talk about what are all the effects. And what they're doing here is not just building this concept map, but this concept map becomes a dynamic simulation, because, as an example, what I'm looking at here is the support by sympathizers. The amount of support by sympathizers that you have is increased when you actually or can be affected by anti-terrorism support by moderate forces. If there's intergroup communication, that could affect it. It could be affected by the political influence of a terrorist network. And then you could assign parameters to each of these particular values and then do a what-if situation. You know, what if terrorism spread that particular way? How could we control it? What would be the factors that affect it? How do we control diabetes in the population? How do we control diabetes in a person, right? So all of those things are happening. And the same thing with agent modeling. There are entire NSF projects that are dedicated to collecting the best examples of agent modeling in particular domains. So for instance, in Iowa, Lee Teftison is creating a project, or has created a project, in which agent modeling for economics has a home, and you can find software, data sets, examples of how economics research is using agent modeling to advance the understanding of economics. Now, one of the things that we've noticed is that computational thinking seems to have these triplets. I've already talked about expectation, observation, and reflection. Another one is excitement, where students actually get excited about doing science computationally. They get experience building models, and that leads to developing real expertise. There's the putting together of the computation as an experiment to support theory. There's the understanding of the application, the algorithm that allows you to implement the application, and the computer architecture that it's running on. I showed you a graph that talked about running models, learning to modify existing models, and then creating your own. We talk a lot about verification. How do you know if it's right? But what I mean by verification is, have you programmed it correctly? What I mean by validation, have you programmed the correct model? So you could have the right model programmed incorrectly, and it would not be, you could look at the science and the equations and say that looks valid, but when you run the code, you can't verify that it's correct. And then accreditation is this model, is this example good for learning something? And then we're going to talk now about the the seventh one of these, which is sooner, more, and better. So let's talk just a bit about parallel thinking as it relates to computational thinking. And in this case, the reality is that the world is parallel. Our math for many years has been sequential. Let me give you an example. In a galaxy, all the stars interact gravitationally at the same time with each and every other star in that galaxy. The stars do not label themselves 1 through n, and then sum themselves in pairs, I less than j, to calculate what is the movement of each star as a result of the gravitational field one star experiences due to the sum of the gravitational fields of everyone else. But mathematically on computers, that's how we tend to calculate the net force on a star, is we sum the individual pair forces. But if we had a computer that was parallel, in which all the processors could talk to all the other processors, you could imagine a world, maybe not today, but soon, in which every processor could take care of one or more stars and could actually compute the interaction in parallel between it and every other star through a network. And there would be some network latency, just as there is in the real world with relativistic effects. Many, many things in the world are parallel. You don't first breathe in, then have your lungs do something, then have something, then have something, then have something. The individual is breathing, heart beating, blood pumping at the same time. You could take an individual amount of air and track its use in the body sequentially, but the body itself is parallel. So my argument is that it's not a matter of porting serial codes and try to get them to speed up through parallel tricks, but the real goal is to rethink and reformulate the science for the new applications, architectures, and algorithms. In the meantime, yes, we can get some speed ups by taking the codes that exist and trying to parallelize them. My argument is that we would do a lot better by rethinking the science from the beginning. Parallelism definitely can affect how you would think about solving a problem. Here's an example. The classical problem of rates that everybody gets in 3rd or 4th grade is if one painter can paint one house in one day, how many houses can 7 painters paint in 1 week? When I gave that to my class here at Wofford College a couple weeks ago, I told them to tell me the answer to this question. If one painter can paint one house in one day, how many houses can 7 painters paint in a week? And I counted to 3 and everybody shouted 49. I said, why? Well, that's 7 times 7. Then I asked them, do you work 7 days a week? So they said, oh, well, then what do you mean by a week? And I said, yeah, but that's not just the main part. What if there was only one paintbrush? What if there were 7 paintbrushes, but only 1 can of paint? What if there were 7 paintbrushes, 7 cans of paint, so each painter can have their own paintbrush and paint, but the houses to be painted were between a couple hundred feet and a couple hundred miles apart? What if when you needed new paint, you had to go to a paint store that was only in one town and there wasn't a distributed number of paint stores? So all of the features that look at network latency, cache, concurrency, resource allocation will change your answer from simply scaling the thing up based on the number of processors and the rate at which each processor can work to all the other aspects of the parallel computer that would affect that. So let's think a little bit about how do we become productive in a computing environment. In physics, we call power work over time. In a computational model, I'm going to rename that productivity. How much work can we get done in a given amount of time? Now, if we do this on a computer that has one processor, well, we're pretty much limited by how much work we can do on that one processor in a certain amount of time. But if I scale that up by a factor S, what if I multiplied both sides of the equation by S, so I am producing a larger amount of work, a larger amount of something? One way to do that is to take the S scaling factor on the right side of the equation and divide the denominator by that factor S. Dividing by a quotient is the same thing by multiplying an inverse. So this is the same thing as multiplying both sides by S. But here, what you can see is that I could think of it as getting the same amount of work done in less time. The time it took before is now reduced by the factor S. If I have 2 processors, I would expect it to be twice as fast. In reality, that's not true, but that's the thinking. The larger the number of processors, the quicker I can get the same amount of work done if I can parallelize the work across all of those processors. Another way to think of it is that I could do one job in an amount of time. So this would be the calculation of the energy of one molecule. But what if you had lots of molecules? Even though in chemistry, as an example, I can't often use that many processors to speed up the chemistry of a small molecule. If I had a computer with lots and lots and lots of processors, maybe I could run a separate copy of the job on every one of those processors. So in the same amount of time, I'm actually getting many more molecules computed. Any given molecule takes the same amount of time, but I get more molecules computed because I can use parallelism to make that happen. Another way to think of it is I could have a model in which it takes much more work, but it's a better model. I can reduce the granularity. I can increase the number of terms. I can increase the number of approximation order so that I get a much better model that gets solved in the same amount of time. Now, of course, none of these three examples of sooner, more, or better are necessarily unique or exclusive. Sometimes part of the code can be run faster. Sometimes you do more copies of the code, and sometimes you do a better code. But these are the ways that we're thinking about productivity, and computational thinking is at the heart of all of this. What are different ways to think about the problem? How could I compute the problem differently to take advantage of more processors, of more memory, of a bigger bandwidth? So the whole idea is, part of the thinking is, to what extent can vectors help? Sometimes there's a type of programming that lends itself to vectors or GPUs, array processors, whatever you call them. Sometimes it will lend itself to multi-core, many-core. And sometimes it's just a matter of thinking about using the computer to get a lot of work done, and it depends on what your data flow is. Right? But all of that is going to be affected by your thinking about the problem and how you're going to solve it. So what have we learned? As we're trying to get to petascale, as I have said often, it is not a coincidence that 5/7 of default is fault. A lot of the issues that people have trouble with are the default random number generator, the default initiation of attached processors, the default memory transfer. All of those things are usually not what you want. And we have to help people think more deeply about how we actually use a given architecture. It's just not true anymore that you can just use the default parameters of a compiler without testing the results of that optimization. A second lesson I like to say is that if we don't model what we teach, we're teaching something else. So if we're doing parallel computing, let's go back and start with the science and go back to the science and not simply get hung up on how fast did the code run. We have to keep asking the question, how do we know if it's right? And especially with a lot of stochastic work, the random number generation is starting to be more and more problematic. Another one is that big data is relative. When you spend more time communicating and moving the data than you do computing once you have it, that's kind of a threshold of big data, right? If the communication costs are negligible, that's not big data. That may be data. You may have a data-driven model, but the big part of big data comes when you really have to start thinking about where is the data physically and how much physical time and level of effort, even the computation that's involved in communicating the data. Do you have to reduce it? When the data comes down from the telescope or down from the satellite, are you going to store all of it, or are you going to do a pre-computation and only store some of the data? Again, mapping the science versus mapping the math, not every parallel system is going to be appropriate for the kinds of problem that you're solving. And then if we're going to make progress, it actually takes a network of villages, and that's the XSEED project. So in terms of resources that are available, I'll make the whole talk available, so all of these will be active links for you, or Steve can send that out. One of them is the XSEED community, and the XSEED community has tutorials, lessons, information about outreach, information about test beds, scientific gateways, technology, ways to access computing in such a way that you can, again, do a lot of computational science education through these gateways. So you don't necessarily have to write the code in order to be able to run it. It may already have been written for you. So Exceed is very much one of the resources. One of the projects of Exceed is HPC University. And HPC University also has information about careers, information for educators, information for students, resources that could be available, training materials that are available. These could be searched, they could be sourced, you could look at different things. You could say, I would like to look for MPI resources that are there. Show me something about MPI. You could come over here and look at OpenACC and search for the things that are there and what types of training are available with OpenACC. So HPC University is another source. Shodor, which is the organization that I direct, originally as part of the National Science Digital Library, has created a pointer of pointers. So we have both the Journal of Computational Science Education, of which Steve is the editor. We also have links to these other resources. So if you remember Shodor, you could get to the Computational Science Reference Desk. From there, you can get to the other resources that are available. There are the petascale modules. So one of the particular projects, the Blue Waters projects, funded the development of 30 different modules that are sort of start to finish ways of introducing topics into the classroom. And these are actually become quite possible. I mean, quite institutionalized. A lot of people have found them to be an easy way to introduce some of the topics. My favorite proof by Google is if we went up here and looked for CUDA matrix multiply, just in Google itself, the number one module that comes back is the Blue Waters petascale module on multiplying with CUDA. So that could be something that you could look at. In addition, we've developed some domain-specific areas. There's computational chemistry for chemistry educators, which includes taking every major software package that we can think of that does computational chemistry and taking the basic lessons that could be taught and providing complete lesson plans for most of those softwares for most of those topics. Some of the topics are not there because it's not appropriate for that topic for that software. Likewise, we have something for biology. So that's pretty much the overview of computational thinking. These are contacts that you could get in touch with through Exceed to help with either content or process in developing curriculum or degree programs. And with that, I'll see if there are any questions or figure out what's next.
Let me remind people, I'll bring up the slide with a few people are tuned into the chat, but not everybody. So if you do have a question, if you would post it to Ajax chat using this link, these instructions, we'll be glad to answer any questions. Don't see any so far, but I'll wait a few minutes since there's a delay. Also, let me point out that all the things that Bob pointed to, we also have at the SIG HPC Education website a list of training and education materials, which has pointers to all the things that Bob had pointed out as well as other things. So that's another way to get to all of these things is just go to the sighpceducation.acm.org and look for the link on training materials, training and education materials, and you can find lots of these collections of materials that can be used in the classroom and training modules that you can find. Still waiting for questions, Bob. I don't see anything yet in the chat area.
What I do in my class is I ask if there are any questions, And if not, then I give them a quiz. So
Well,
I say, if you don't have questions, then I do.
Yeah.
And then amazingly, after 1 or 2 classes, they start asking questions.
Well, since our viewers are remote and we can't punish them by changing their grade, I don't think that's going to work here.
No, but it's just a motivation, is just to try to get people to ask. And then, of course, I'm available at any time for questions through email. I could set up individual Google Chats. I also have a small budget as part of Exceed to make campus visits. I know Exceed has some funding to help with campus visits and then training and workshops for faculty. And then postdocs and grad students can attend those workshops when they're organized for faculty. We haven't historically organized workshops for postdocs and graduates directly, but they've been welcome at all of the workshops that we've had.
So we'll wait another minute or two just to see if there are any further questions for Bob. So Bob, you mentioned these workshops. Have you decided, I know they've been in-person workshops over the summer in the past. Do you know how that's going to proceed this year?
I don't have absolute knowledge. I know that there will be at least a couple of in-person, but there will be less travel support. So we will have some workshops because we know that some people want to have a workshop, but we won't be able to pay for housing, for instance, for people who are not from that campus or not within driving distance of that campus. But we'll also be developing other types of communication channels. So for instance, a series of talks on a series of topics like what we did today is the introduction, that there will be online webinar mediated training that will go on, some of it during the spring and some of it during the summer. But we're going to need to also experiment with the difference between synchronous and asynchronous use of the same technology. But we do know that there are several campuses that want to host and have enough critical mass of faculty that would make a good location, and we have enough funding to put an instructor on that campus. We just don't have enough to pay for the kinds of housing and meals that we've been paying for in the past.
So when you have that organized, you'll be posting that on the Exceed site somewhere?
It'll be posted on Exceed. It'll be posted on Nixie, HBCU, and I'll send it to you to post it on SIG HPC as well.
Okay, good. Well, it doesn't look like there are questions, so let me thank you for giving the webinar. I think it was a nice introduction to computational thinking, and I hope that people will take advantage of the links that you've given them and look out for these workshops in the future if they're interested in introducing it into their own classrooms. So with that, I think we'll end the broadcast today and thank everybody for attending.
Great. Thank you.